All right. 5, 6, and 7. You want to go over those? Do you have any particular questions that you want to deal with before we jump into sort of the different topics? Yeah, Kyler?
For exam, to read like all of 50, number 14.
This should be in the back of your workbook. Number 15. You're going to see a problem, something similar to this. Not exactly like this, but there were several questions like this in the concept test, and you should go into the concept test. The key here is that you have uranium nucleus at rest, so no momentum. Then it splits into two pieces.
No, there's number 15.
Huh?
I think it's number 15.
Was that number 15?
Yes.
You said 15?
No, I said it would fall to 15, number 14.
Oh, number 14. Okay. But that next one's a good one, too.
Oh, yeah.
All right. This is a good one, too. I mean, I told you it's going to be in there. It will be on there. On this one, you think, oh, gosh, this is momentum. Is it conservation momentum where I say Pi equals Pf, or is it that F equals delta P over delta T? And the reason I know it's delta P over delta T is because, well, this one's not asking for the force, but I only have one object that's really involved. So even though it's a collision, it's not a collision between two objects that move off in different directions. You could see this in a couple different ways. I could ask you for the force, delta P over delta T, but in this case I asked not for the force, but the magnitude and the change of the momentum. That's the delta P. So it's just knowing the vocabulary, right, the language that we ask for. So I find my delta P is M times Vf minus Vi. M is 0.1 kilograms. That's given right up here. Vf minus Vi. This is where you have to be careful. And anytime you have something that reverses direction, just add them up, because it's going to be 14 minus negative 6. So I just add those.
So if it reverses?
If it reverses,
Yeah.
right, just add them up, because remember you're going to be changing signs in there.
Okay.
All right? And so that's 0.1 times 20, so B is the right answer. All right? Any other particular questions? Would y'all rather go through all the topics, or we can just sort of go through the exam and look at questions and work through some? What would be better for you guys? Go through the topics? Is that okay? And we'll work some problems too, okay? So we already did chapter 8, those 3 questions from chapter 8. But chapter 5 was work and energy. Remember, work is force times displacement. You will have some where you just have to calculate the work. Remember, look back at your OpenStax quizzes. I pulled 4 or 5 questions on the exam from those. So there, you already know 3 questions from chapter 8, and now you know another 4 questions. So that's a third of the exam. So look back at those OpenStax quizzes. They're not the most difficult questions. I didn't pull those. That would be kind of mean. But some of them were challenging. So look back and make sure that you understand those questions on the OpenStax. On the homework, too, you'll see questions like from the homework as well. I mean, you look back at the old tests, there are a lot of homework-like questions. So be able to know how to calculate work. It's the force times the displacement. Also know that, you know, if I have a force in one direction and a displacement in the same direction, that's positive work. If they're opposite, that's negative work. You've seen questions like that, like where I have, you know, a force in this direction, but I tell you the displacement is in that direction, that's a negative work. Also, if the force is at an angle, that force would also be doing negative work, because the component of the force that does work, which is that component, is opposite the displacement. That's the key, that it's opposite the displacement. Also know the work-energy theorem. All right, work-energy theorem, if I do work on an object, then I take away energy. Like, for example, if I have an object that's traveling, say with a certain speed, I don't know, 2 meters per second, and it has a mass of 1 kilogram, that object has a kinetic energy of 1/2 mv squared. 1/2 of 1 times 2 squared, so that's 2 joules. It has 2 joules of energy. And then let's say that on this surface, I have a kinetic frictional force equal to, I don't know, 0.5 newtons. And how far would it take for that object to stop? Would you know how to work that? We've had various problems like this, but this object is going to travel along this frictional surface, and that frictional force is going to take away energy from that object. It has an energy of 2 joules, and it's going to stop when all of that is taken away. So I say the kinetic friction times the distance that it travels. So 2 joules equals 0.5 newtons times d, and so d equals 4 meters. You don't have a problem just like that, but you do have a question, a couple questions where you're dealing with the work energy theorem, where if I do work on an object, I change its energy. If it's something like friction, I'm taking away energy. If it's something like a force that I'm pushing on, then I'm giving it energy. Okay? Of course, you're going to have the roller coaster problem, like we had in homework and on the old tests and stuff. So a problem like this, where I give you some object, it will either be at rest or moving, but make sure you read the problem and make sure that you know what it's doing. Sarah?
So initially, it's just at rest, all it has is potential energy.
Right. If V equals 0, PE equals 0. However, if V is greater than 0, then PE is greater than 0. You need to read the problem and make sure, see which it is. Does it have kinetic and potential, or does it just have potential?
So if you give us a velocity at the start, it has both potential and kinetic.
That's correct. Yeah. In general, if it's moving, it has kinetic energy. If it's not moving, it has only potential. And then you should be able to tell me what is the speed here. All right. What is the speed here? And then if it comes up to a rest up here, what height does it come to rest at up there? So for example, let's, I don't know, let's just take this one. Let's say that this height is 2 meters, and this height is 3 meters. I would ask, what is the speed at that first hill, okay? In which case you would say, well, the total energy here, which is 1/2 mv squared plus mgh, is equal to the total energy here, which is 1/2 mv squared plus mgh, realizing that those v's and h's are different. So I can get rid of my m's here, 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 and here, and I get 1/2 of, let's say that v is equal to 2 meters per second, 2 squared plus 10 times 3 plus 1 equals to 1/2 v squared plus 10 times 2. And then you'd solve that for v. Okay? You will have a problem like that. You'll also have some conceptual problems where I just ask, does it have kinetic or potential energy here? Does it have kinetic or potential energy here? What's the speed like? Is it moving? Is it moving fast? Is it moving slower? Is it moving faster here or here? Which is it? Is it moving faster here or here? This one or this one? The first one or the second one? Is it moving faster here or here? And then you ask yourself, well, where does it have more kinetic energy? Where does it have more kinetic energy? The high hill or the short hill? It's the short hill, right? Because it has a lot of potential here, less potential, so it has more kinetic. Remember, the sum of those is always going to add up. So if one goes up, the other goes down. You'll have a couple problems dealing with that type of issue. Let's see, what else in chapter 5? Oh, springs also. So remember that if I compress a spring, I think you had a couple questions regarding this, actually. There are 27 questions on the test, by the way. So if I have a spring and I compress it from its equilibrium position, then I give it elastic potential energy. And we had some problems that we worked in the workbook or in the homework that if I let all of that elastic potential energy go into kinetic energy, say I ask, what is the speed of this block if its mass is 1 kilogram and the displacement, that is how much I've compressed that spring, is say, I don't know, 1 meter, for example. How fast is it going? Then I would set the elastic potential energy, 1/2 kx squared, equal to the kinetic energy, 1/2 mv squared. It's like a spring-loaded gun, right? I give it a bunch of energy right here by compressing it, and then I let it go, and then this thing comes off traveling at a certain speed. I can let all that elastic potential energy go into kinetic energy. And then I should be able to solve this, get rid of my halves, they cancel. We also need to know our k value. Let's say k is 100. So we get 100 times 1 meter squared equals 1 kilogram times v squared. And so that's v equal 10. Okay? You will have a spring dealing with elastic potential energy. Again, I don't remember if I put Hooke's law in there. I'm pretty sure I didn't. But if your spring compresses a certain amount, you should know how to calculate the force. I think I didn't put it on there, but I don't remember. Okay? The negative just deals with the direction. So, yeah, it is supposed to be a negative. But that just says that if I compress it in this direction, the spring pushes back in this direction. So I like to just use my intuition about the spring. Which direction is the spring going to push? But not a big deal for this exam. Okay. You will see springs. I think there are 2 questions on that. At least 1, maybe 2. And there's no power on it. I think I told y'all. There is no power. All right. And then chapter 6. Any questions about chapter 5? Let's just sort of peruse that old exam. Was this fall 14 or 15?
Fall 15.
This is fall 15. You're going to have the equation sheet. So that equation sheet is right here. So those are all the formulae for chapter 5. There's our work formula. There's our kinetic and potential energy. That's conservation of energy. Energy initial is energy final. This is Hooke's law. This is elastic potential energy, and then this is power, work over time. Second one, and it's your name, Gavin. I was gonna say Gavin. Smith.
Do we have to print it out or?
No, I'll bring it to you. It'll be on the back of your form. So your bubble form, on the back of it, have your equations. Okay. But you should know what's on there. Just be familiar with it. Just, look over it. Make sure that you know what's on there. Okay. Like here's a spring question. Yeah. Number 8. You want me to work number 8? Yeah, it's the same problem. You want me to work it? Okay. So here I have, this is the mass of my car. This is its speed, so it has a kinetic energy equal to 1/2 mv squared. And then it goes into a spring that has a spring constant, and it compresses that spring, giving all of its energy to the spring, which is 1/2 kx squared. And here it's asking you to solve now for x. So I get rid of my halves. I have the mass, which is 10. Gavin, did you have a question? That's your k, right. Your spring constant is your k value. That's 250 times x squared. And then you solve for x. It turns out to be 10 times 25, 250. $125?
Yes, because I do this problem every time, and then I think I get it wrong, and you just like rounded it off to.
Right, to 2 sig figs. 10 times 25 is 250. Why is it not 1? I'm confused. Oh, it's asking for the total potential energy. I thought it was asking for x. By the way, if you were solving for x, it would be 1 meter. You'll follow? But it's asking here for the potential energy, and that potential energy is 1/2 kx squared, which is 1/2 times 250 times, or excuse me, you could just say 1/2 times 10 times 5 squared, which is 125 or 130. Y'all see what I did there? I don't know the x for this, so I say, well, my kinetic energy, 1/2 mv squared, is equal to the total energy in the system. Okay? Y'all clear with me? Good? Great. All right. Not an easy exam, but it's easier than previous exams, I think. Oh, here, this question was asking, what is the compression? You need to know your conservative and non-conservative, what that means, right? Conservative forces conserve energy. Conservative forces include field forces. Conservative forces are path, which is it independent or dependent? That's right. It doesn't matter the path you take. They're independent of the path. Okay? That's it for Chapter 5. Let's look at Chapter 6. Any other questions though for Chapter 5? All right. Let's look at Chapter 6 then. Chapter 6, really 2 classes of problems. And you'll see a couple of collisions. You'll see F equals delta P over delta T. I think there's a perfectly inelastic collision. That's just where they stick together, you know. You need to know elastic versus inelastic, what that means. But you have collisions. That's where you use this PI equals PF. I'll work one. And then you'll also have this F equals delta P over delta T. We worked one of these earlier. But you know the difference in these because these will involve a collision between 2 particles that collide and then move off in different directions. This will involve a collision, but one particle against another stationary object. Like you know, the football player catching the ball, the football player doesn't move, the car running into the wall doesn't move. That's for business. And also usually we'll be asking for the force. As we saw in that previous problem, we also asked for the delta P. So to be aware of sort of how this business works and be able to be flexible in what you can solve for. Well, as I said, you need to know elastic versus inelastic. Elastic collisions conserve energy. They're really bouncy, and so they conserve a lot of energy. And inelastic only conserve momentum. Actually, all collisions conserve momentum, so elastic conserve energy and momentum. But we usually just say that elastic conserves energy, but it also does conserve momentum, because everything conserves momentum. No matter what kind of collision it is, no matter how messy it is, it'll always conserve momentum. Let me double check. You need to know about the vector nature of momentum. We had a couple questions like that in the concept test. And then that's it. Let's look at a couple of examples. So there are 2 collisions. One will have a nice pretty picture like this, another will have it'll be described in words. So make sure, you look back actually at the OpenStax question, that was one of your OpenStax questions. It was a collision, it just described it in words. You follow what I'm saying? No pretty picture, which I like the picture, but it's good to be able to read the problem and translate it into a physical scenario. So here, before collision and after collision, I want to know the magnitude of the final velocity. I say the initial momentum is equal to 2 times 4, that's 8, plus 4 times minus 3, so that's minus 12. Momentum is mass times velocity, but velocity is a vector, so I have to include the sign here. Be careful, because if you don't include the sign, you know that's going to be one of the options. If you get the signs wrong, that'll be one of the options. That'll be sort of the distractor. So be careful that you get that sign right, because I'm already looking for that particularly. 8 minus 12, so my momentum up here is negative 4. And then I set that equal to the final momentum, so I get negative 4 equals to the combined mass, which is 6 kilograms, times VF, V2F, or just VF really. And so it's negative 4 over 6, which is 0.67. It was just looking for the magnitude, but if I'm asking for the velocity, I'll say it's going to the left or to the right. All right, just one dimension, not 2 dimensions. Kevin?
So you're just multiplying the 2, the velocity and the mass together?
That's right. Momentum is mass times velocity. I'm adding them, but because this is a negative velocity, it's to the left, that's why I have this negative here. So I get 2 times 4 is 8, 3 times 4 is 12, but this is to the left, so it's minus 12. All right? Answer comes out to be minus, or 0.67. It's actually negative 0.67. 4 divided by 6 is 2/3. Kyle?
So why is the 3 is negative because it's going in the opposite direction?
Because it's going to the left. Remember, right is positive, left is negative. All right? Yeah, Gavin?
The last part right there, the -4, that's your answer you get when you subtract 8 as well. Equals 6.
Right, yeah, 8 minus 12 here. That's PI is -4. And then I use this 6 because my 2 and my 4 kilogram now stick together, and they're both moving off at the same speed at this 0.67 meters per second. Okie dokie, folks. Okay, you will also have, clear? We good? Okay, you also have a problem. I like this number 13 or something similar, you know. I have this ball that's being dropped onto a steel plate. There's its speed after impact, before impact. The ball is in contact for 0.03 seconds. What is the force? What is the force? Well, F is equal to delta P over delta T. All right, I'm usually looking for the magnitude here, so you don't really need to worry so much about signs, but realize that it does change directions. And as I said before, if it changes directions, what do you do for this difference? You just add them up, right? The reason is that I get m times the final velocity, which is 4.2. The initial velocity is negative 4.5. I get 4.2 minus negative 4.5. And if they switch directions, you're always going to add those numbers up. So, and that's usually the case. Divided by 0.03. This was 0.3 kilograms. It's 8.7. I don't know. It is what it is. But that value, I don't know. Does anybody know what that is? It is 87. Okay. 87 newtons. You'll have, I think there's just one like that. All right. And that's it for chapter 6. Let's look at chapter 7. May I go away from here? Well, let's just sort of look back at some of these. Let's see, this is from a concept test question. You want to look back through the concept test. Now, like the uranium nucleus, all this business about P equals MV, all of these are good. I would look back through your concept test. Look at the old test too, but print out those 6. Goodness. Print out the slides. I like to do 6 to a page, and then you can fold them in half and you can sort of quiz yourself on them because the answers are on one side and the questions are on the other. Just print them out in black and white or whatever. Save your ink. All right. Chapter 7. You're going to have a couple of conversion type things where you're converting from one system to another. So be very careful. Remember, you'll never go wrong converting it to radians. It's not, usually you can keep it in whatever you're doing, but you'll never go wrong converting it to radians. Chapter 7. You had, I say, conversions, radians, revolutions, degrees, 2 pi, 1, 360. Those are our conversion factors. Remember, our notation is that if it's clockwise, it is negative. If it's counterclockwise, that motion is positive. That rotation is positive. That's just a notation that we take. You're going to have a couple of kinematics problems where you're using this omega equals omega naught plus alpha t, or theta equals omega naught t plus 1/2 alpha t squared. You had several like this in the recent quiz, so I think I actually pulled one from there. But where you're solving for some unknown, given, say, alpha and t, you have to find omega, or something along those lines. Those are hard if you don't know how to do them, but if you know how to read the problem and pick out what is what, then they're largely just plugging into the formula. So with some practice, you'll be able to read through and say, oh, it's at rest. That means omega naught is 0. Or, oh, it says it's accelerating. That means alpha is whatever it says it is. Okay, and theta is the displacement or the angle through which it turns. You want to be looking for those words to describe those variables. That comes with practice. Just make sure that you know those.
So with the conversions, just out of curiosity, I know somebody brought it up in class. Was that where the tornado problem came in, like having to convert? Because it only really gave the diameter of the tornado and it gave like the velocity.
You want me to show you all the tornado problem? Because people, gosh, I thought it was really difficult. And let me show you, because once I show you, you're going to think it's really easy. Here's your tornado, right? I think it said that this was like, yeah, it was 60 meters in diameter. And it was going like 200 kilometers per hour. That was how many meters per second?
I think it's 500 kilometers per hour.
Okay, I'll say 40 meters per second. All right, just so I convert that to meters per second. And then it asked, what is omega equal to in revolutions per second? So there are two steps to this. The first one is that you had to figure out what omega is in radians per second. So you say V is equal to omega R. V was 40. Omega R is 30 meters. So omega is 1.3. That's in radians per second. These aren't the numbers, by the way, that were, I don't think. Are they? No, the 40 is different. All right, so 1.3 radians per second. And then you have to convert that to revolutions. 2 pi, 1 revolution. There are 1 revolution to 2 pi radians, so my radians cancel. And I'm left with 1.3 over 2 pi, which is not very big. I mean, it's less than a revolution per second. I get 0.2 revolutions per second. So they move pretty slowly, actually. They have horrendous winds, but they actually rotate fairly slowly. They don't have to rotate very big because they're so big, they're so wide across. All right?
So if you're going from a degree or a revolution to a radian, well, if you're going from a revolution to a radian, you multiply by 2 pi.
I guess. If you're going from radians to revolutions, you divide by 2 pi.
Most of the time, it seems like most of the time you're going from revolution to radian.
Right, yeah. But if you're going from radians to revolutions, is that what you're asking?
No, also revolution.
Revolution to radian? Yeah, I don't know. Gosh, I guess. Let's see. So 1 revolution, in 1 revolution, there are 2 pi radians, yeah. I always just have to write up my conversion factor. I wouldn't try to memorize that. I would just, look at your units. These units cancel, and they make you with radians. All right? But you will have questions like that. Okay? Yeah, that's 0.2. 1.3 over 2 pi. That's not what you got, is it? Okay, be careful. I said this to my in-class section. Because on your calculator, if you're doing this, I've had about a half dozen people making this mistake. And this calculation is going to come up where you divide it by 2 pi. You do 1.3 divided by parentheses 2 pi. All right? Because otherwise, you're doing 1.3 divided by 2, which is like 0.6 something, times pi. So you have to, in your calculator, if you have a TI or whatever, you have to put this in parentheses. Or do it in pieces. Do 1.3 divided by 2, answer, divided by pi. And it'll give you 0.2. Be careful. It comes up several times, that calculation. So make sure. It's a very common mistake. For just your order of operations, don't miss a question just because of the calculator thing. That's frustrating, isn't it? All right. Also, centripetal forces. Know what provides the centripetal force. So I'll give you some scenarios, and I'll ask you, what is the centripetal force in this case? So 3 examples, for example. If I have a ball on a string, like in the homework, that's going around over my head, the centripetal force is provided by the tension in the string. Or also, like in the homework, a car going around a curve, the centripetal force is provided by the friction on the road, right, between the tires and the road. are like in, I said that fair ride that spins you around, are like a centrifuge or whatever. The centripetal force is what? The normal force. The wall pushes against your back in order to make you go in that circular pattern. Y'all ever read one of those? Have you? I hate those. It was terrifying.
Literally, I think the worst case scenario flies off.
Well, the centripetal force is, in that case, the normal force, or the force of the wall pushing on your back. Be able to calculate the centripetal force, mv squared over r, or if you don't know v, if you instead you know omega, m omega squared r. Both of these are on your equation sheet. Now, here, be careful, omega must be in radians per second. So if you have any doubts, ever have doubts, just convert everything to radians per second. But like your kinematics equations, that theta equals omega naught t plus 1 half alpha t squared, you don't have to convert it to radians for that. Your units all follow through, but here you must convert it to radians. Yeah.
I thought omega and velocity were exactly the same. They're both in meters per second.
They're not meters per second. So v and omega are similar. Like the kinematics equations, they look the same, right? Except I just replaced v now with omega. But omega is not the same as v. It is an angular velocity, not a linear velocity. It tells how fast something goes around, not how fast something travels.
Theta is angular velocity.
No, theta is angular displacement. It's, the distance. It's not really a distance, but the displacement that you travel through. Omega, that's this curly W, is angular velocity. All right, but they're not the same. They're very similar, so we sort of talk about them in the same way, but they're not the same. They have different units. And that's why here, this equation doesn't look the same. But remember, they are related, like in the tornado question. V is equal to omega times r. And in the concept test and in the homework, that comes up several times, and it'll come up on the exam too. Being able to relate, especially for the velocities, the angular and linear quantities. Okay? Don't forget, omega needs to be in what? Radians per second. In fact, if you're ever in doubt, just convert everything to radians. But you don't really want to be in doubt. You want to know.
Velocity is constant. Omega is constant. How does the acceleration, the angular acceleration relate?
Yeah, so if omega is constant, then alpha is equal to 0. Right? Right. We said a similar thing. If v is constant, a equals 0. These are rates of changes. So alpha, the angular acceleration, describes how omega changes. And so if omega is not changing, alpha is equal to 0. We said a similar thing here, that if v is constant, a is equal to 0.
Will centripetal acceleration be on it?
It could be, yeah. I don't think it is.
It's not in my equation sheet, but
Is it not?
it's the same.
It sort of is. Let me show you how. Because I understand that it's not written on there. But F equals ma. Our centripetal force equals mv squared over r. This is on the equation sheet. But notice that that is my acceleration. The centripetal acceleration is v squared over r, but it's not on there. But you will have to calculate a centripetal force. I think there's one calculation for the centripetal force. There might be two, and then there are a couple of conceptual questions. I think there's just one. Okay. I will check my notes. I think that was it. We can look at do some conversions, some kinematics, and centripetal forces. And then those 3 problems like we did in the beginning for Chapter 8. If y'all weren't here, I recorded it, or we went over it, but you'll have 3 problems from Chapter 8. Were you here, Gavin? Okay. We just recap those. They'll be on the video. But you'll have 3 problems from Chapter 8. One where you add up the torques. You have to find the net torque. It'll be practically just like this, okay? 2, where you have to figure out the net, or the balancing, right? Thank you. So how you have to balance the seesaw, just like we did in lab. So I have it pivoting here. I asked, where does this thing need to go on this side in order to balance this side? You set the torques equal to one another, and then I'll give you a series of images that have an object that have different forces on it, and I'll ask you to rank them according to their torques, either from greatest to least or least to greatest, I forget. You do have all 3 of those questions on there. Okay, so make sure that you're ready for those. They're like this in the homework, in the practice test, in the workbook. There's some like this in the previous one, the net torque. It's a homework problem. There's practice test in the workbook and in the old exams. And then this one, these are in the concept test, which are on Moodle, or on the website, you know. Okay, let's just sort of peruse through this exam. Well, there's a conversion. Yeah.
25 on that exam was when I saw
Yeah, the linear velocity does not change. And this goes how, they're not equal, but they're related. So V is equal to omega times R. And so since alpha equals 0, omega is constant. And if omega is a constant, that means that V is also constant. So it is the linear velocity does not change. These others are not correct. The linear velocity equals the angular acceleration. That doesn't even, not even close to this thing. The linear velocity is changing constantly. So if we just said that it's not changing, linear velocity does not change. Oh wait, is the answer C? It is C actually, yeah.
Oh, that's good.
I'm sorry. The magnitude of the velocity doesn't change, but the velocity does change. Why does the velocity change in this case? Because you're spinning, right. So what does that mean if you're spinning? Why is the velocity changing? Let me draw a picture. If I have, that's right, Ling Ling. So if I have this velocity here, it's always the same magnitude, but it's also constantly changing direction. That's why we need that centripetal acceleration, because if we didn't have that centripetal acceleration, this velocity vector would just keep going straight in a straight path. Okay, I'm sorry I messed it up.
If you were to like go with the thing that's spinning, would it have a constant velocity?
It would have a constant velocity. That means that it would have a constant speed in the same direction. It would not change direction. So if I spin it around and you let it go, it goes in a straight line. There was a question like that, I think, in the workbook and in some of the old tests. All right. Any others from these? Or another exam? Look, here's some relationship type things. You'll have that. Not like, you know, guy meets lady. What do they do? No. But like this, a mathematical thing.
I have a question about when momentum is at 0, what is, it's a question when your momentum is 0, what is,
Oh, what is your kinetic energy?
yeah.
Yeah, so momentum is a vector quantity. So if I have 2 particles, imagine 2 particles here and here. Let's imagine that they have velocities that are in opposite directions. Then in this case, if the mass and the speeds are the same, the net momentum equals 0. Because look, these represent the momentum vectors, and so they add up equal to 0. Because, you know, they add up like vectors, they cancel out. However, the kinetic energy, because these things are moving, the kinetic energy is greater than 0. However, the reverse is not quite the same. If the kinetic energy is 0, that means kinetic energy is scalar. If the kinetic energy is 0, that means none of the particles are moving. And in that case, the momentum has to be 0. All right? If the momentum is 0, the kinetic energy might be 0, or it could be bigger than 0. Because another way to have 0 momentum is to have 2 particles that are just sitting there, not moving at all. And those particles also have 0 momentum. But the point is that if they're going in opposite directions, they have 0 momentum, but they're still moving. Is that clear, Sarah?
I have a question for number 2 on chapter 7.
Okay. Okay. Number 2. Okay, so when I start reading this, I just start, Potter's wheel moves from rest, that says omega naught equals 0, to an angular speed of 0.2 revolutions per second. So omega, or omega final, is 0.2 revolutions per second, and the time is 30 seconds. So that looks like all we know, and I want to know what is alpha. That's my angular acceleration. I like going through this process. Like I come to this problem, I don't know right off how to work it until I write down everything that I know and everything that I want to know. And so I look at these and I see a pattern, so I think, I think I can use this in order to solve for alpha. So I say alpha equals omega minus omega naught over t. Omega naught is 0 because it was at rest, so it's 0.2 divided by 30. And that is 0.007. But that's not the answer because that is in revolutions per second. And so now you need to convert it to radians per second. I say 1 revolution times 2 pi, 0.04, thank you, 0.04 radians per second. Yeah, you could convert it first. I wouldn't recommend that though because then you have to, oh no, yeah, it's the same. Yeah, you could convert it first. It would be the same. You would just have a factor of 2 pi, where, right here. Multiply that times 2 pi. That'd be fine.
If I do the problem, I'm going to put that first answer as the answer. I'll just get to the counter.
Right, and you know that's going to be an option too, right? At 0.007.
Yeah.
You just roll your eyes at me.
No.
Okay. I'm sorry. That's a good test that you have answers that are common mistakes. So, you know, that's just good testing. Try it. But you know that, so you need to be certain that even if I get an answer, you ask yourself, really, how do I do that? Am I really certain? But you know, don't second guess yourself too much. So I did read a study this week that they found that students who change their answers more often get the answers right than get them wrong, which is sort of opposite of what most people have thought, what people have always told me, that never change your answer. Okay? What else, y'all? More questions? Not an easy exam.
You won't give us like 2 days.
No substitution. Like that dentist grill. Yeah, no, the kinematics, I don't want to say they're easy, but they're one-step problems, right? They're one-step, or you might have to do a conversion, but there's no substitution of one equation into the other. All right, is that happy?
Yeah, I watched your video on that one. I was like,
That dentist drill? Yeah, that's a nightmare, wasn't it? Okay. All right, folks. Anything else? No? Yeah, I'll go over 8. Listen, y'all go if you want, but I'm going to go over 8 for Gavin and anybody else that came in late, okay? But I'm going to keep this recording. You're welcome to go or you're welcome to stay. So in chapter 8, you'll have 3 problems. It's really just like the first few pages of chapter 8 in that workbook. The first problem is you'll have to find the net torque. I'll ask you, what is the net torque? I'll give you a bar. It'll look a lot like this. I'll give you some axis of rotation, say the axis of rotation is right there. And then I'll draw several vectors on it. I give you 3, but I'm going to draw 4 here. I'll give you a force vector there. Let's say it's 2 newtons. I'll give you a force vector here. Let's say this is 3 newtons. 1 here. Say that's 1 newton. And 1 here. Say that's 2 newtons. And then I'll give you distances. So I'll tell you, for example, this is 2 meters. This is 3 meters. And in some way I'll tell you, this is 1 meter. So you can know the various distances to where those forces are applied. You need to go through first and figure out which forces do not provide a torque. Now torque equals Fr sine theta. F is the force, R is the distance from where the force is applied to the axis of rotation. So in this case it's 1 meter. And then theta is the angle between them, which will be given. So for example, right here, theta we'll say is 30 degrees. So if theta is equal to 0, sine of 0 is 0. So over here, theta equals 0, or you can think of it as 180. And so this force provides no torque because theta is equal to 0. It's like trying to open the door or trying to make the door move by pushing in this direction. I'm never going to make it move in an angular direction. The other force that provides no torque is the 2, 3, or 1. The 1, right, it's like trying to make the door move by pushing right here. I'm never going to make this door move pushing at the hinge because R is equal to 0. So I can get rid of this one too. The next step is to figure out which are positive and which are negative. Remember, clockwise is negative, counterclockwise is positive. So these forces right here, this force considered all by itself around this axis of rotation will cause it to move in this direction. That's what? That's negative, that's clockwise. What about this force? Also negative, right? It also makes it go in this direction. If I had a force over here pointing up, that would be positive. It would be counterclockwise. So you want to figure out which torques are negative and positive. In this case, they're both negative. And so the sum of my torques is negative torque 1 minus torque 2, because they're both negative. And then I calculate their magnitudes. 2 newtons times 2 meters. That's this distance from here to here. Theta is 90, sine of 90 is 1, so I'll leave that out. Minus 3 newtons times 1 meter times sine of 30. What's that? 4 minus 2.5. 2.5 Newton meters in the clockwise direction. I know it's clockwise because it's negative. Okay. The 2 Newton force is right here. The distance to the axis of rotation right here is 2 meters. The 3 Newton force is right here. The distance to the axis of rotation is 1 meter. Yeah. It'll be a little more clear. But there's a homework problem just like this. Mackenzie?
What is it theta from the torque point? Oh, I see it. Wait, no.
Oh, yes. Thank you. I made a mistake.
How are they both clockwise?
Just a second, Sam. I'll tell you. So I have negative 4, so it's minus 6.5. Thank you. Okay? They're both clockwise. These two are both clockwise. Well, if I pull up here, I make it move in that direction. You see that? But this one is clockwise. The other one, even though it's at an angle, it's going to cause similar rotation. So even if I pull at an angle, I'm still making it go in the clockwise direction. This one right here. Because the axis of rotation is right here. The object is going to travel in the direction of the force. So if this one's pointing up, this side of the object is going to go up. If there's one pointing up over here, it'll go up. If there's a force pulling down here, think about it, don't answer. If I have a force pulling down here, clockwise or counterclockwise? Clockwise is right. Right. Because it would make it go in this direction. Did I do this right?
I took 5.5, but I don't know if I'm.
4.
Wilson, 1.5.
Yes, you're right. I'm sorry. 2 minus 5.5. I was trying to do it in my head. Not accurate. All right. Now, that's the first problem. Kevin?
R, that part, R is the distance.
Right. From the axis of rotation to the where the force is applied. The second problem, I'll give you a seesaw like this. You'll have some mass over here, say 2 kilograms at 3 meters. And I want you tell me where I put a, I don't know, 1.5 kilogram mass on this side in order to balance it. You say 1.5 times R equals to 2 times 3. So R is equal to 6 over 1.5. Oh, yeah, so I'm sorry. That's what it would be. It would be a value less than 3. But you get the idea. I'm setting the torque equal. The torque on this side is equal to the torque on this side. This is the force. I canceled out my G because it's actually M times G. If you have a G on both sides, the mass times the acceleration due to gravity times R. M times G times R is equal to M times G times R.
Would it work the same way if the pivot point wasn't in the middle?
It would not work the same way, but the pivot point will be in the middle.
Okay, because I thought you said it would be in points.
No, I said it wouldn't.
Okay.
Yeah. I said it wouldn't be, like in lab, we have the pivot point set off to the side. You're not in lab, right? Yeah, center of gravity stuff. We're not going to see that. It'll be in the middle of the board. The R is still the torque, so it's from the axis of rotation. Yeah, so let's say that the board is actually bigger, right? And I have the 2 kilogram mass at 3 meters, and I ask, where can I put this 1.5 kilogram mass? That means that I would have to put the 1.5 kilogram mass at 4 meters. Right there. Right, 4 meters from the axis of rotation. And then the last thing that you'll see is I'll give you, like in the concept test, I'll give you several objects that are all rotate about the same axis, and I'll give you some forces. And I'll ask you to rank them from biggest to smallest torque. This one, the biggest torque, would be right here, because it's the biggest force that's at the furthest moment arm, the furthest from the axis of rotation. This would be the next biggest force. It's still a big force, but it's at an angle, so you get less of the force actually provides torque. And then this small force at a small moment arm would be the smaller torques. There were several variations of that on the concept test that we worked. That's downloaded, you can find it, and you can also see it. I don't know if we had it in the workbook, but it was in the concept test questions. Those are the 3 questions. They come at the end.
I think the third one would be smaller.
No, I understand what you're saying, but no. No, we'd just be looking at the magnitude. All right? Okay? That's good thinking, man. Is that all, y'all? Yeah?